Welcome back to the Explainer. So today we're looking at something absolutely fascinating. We've managed to get our hands on this series of really intricate, handwritten notes that propose something, well, honestly, it's almost unheard of. They're taking the mind-bending complexity of quantum computing and trying to boil it all the way down to a basic physical grid. The whole idea here is to strip away all that intimidating physics and just focus on the absolute basis of computational logic. It's all about finding simplicity in something incredibly complex.
Which brings up a pretty wild, provocative question. Can simple punch cards actually run quantum computers? I mean, when we normally hear the phrase quantum computing, we picture those massive supercooled cylinders in multi-billion-dollar labs, right? It runs on physics that basically feels like magic. But the source material we're decoding today, it attempts to make the basis of quantum superpositions incredibly simple. It's actually bringing it back to a tactile, almost vintage era of computing.
Now, what's really interesting about this slide is the signature and the date right at the very bottom. Rupesh Malpani, May 31, 2026. So this is a highly ambitious, forward-looking theoretical document. You can practically see the rapid flow of ideas on the page. The author is laying out this massive goal to build a personal quantum computer, and they're doing it by using really relatable analogies and foundational concepts. It is a super bold attempt to rethink hardware completely from the ground up, starting with just the absolute basics.
Okay, to make sense of these dense notes, we're going to peel this back step by step. First, the coin toss analogy. Second, decoding Qxbin theory. Third, the math of superposition. Fourth, the magnetic punch card. And finally, number 5, personal quantum computers.
Okay, let's dive into this. Section 1, the coin toss analogy.
To really understand quantum logic, we first have to ground ourselves in classical logic. So the author starts with the most basic, undeniable form of computing we have, which is binary. As the notes say, in the world where a coin toss can be a representation for binary compute, and this is just brilliant in its simplicity. Think about it. A coin toss gives you heads or tails, right? Essentially a 1 or a 0. That single flip is literally the basis of every classical computer sitting on our desks today. The author uses this super relatable analogy to set the stage, just making absolutely sure we grasp the simplest possible binary state before we take that big quantum leap.
Moving on to Section 2, decoding Qxbin theory.
So this is where the author elevates that simple binary coin toss into the quantum realm. Looking at the original Qxbin title page from the source documents, you can see the handwriting is, well, it's pretty dense, right? It's filled with specialized notation. But don't worry, that's exactly why we're doing this explainer. We're going to translate the core message of this specific page right now. Basically, what the author is attempting to do is fuse standard binary logic with quantum states, creating this unique hybrid concept that they call Qxbin.
So the absolutely crucial point is captured right in the middle of the page. The author writes about the application of a positive and negative degree of power to record quantum superpositions on a punch card format simplicity. I love that. Notice that brilliant juxtaposition there. They're taking quantum superpositions, the ability for a system to exist in multiple states all at once, and they are forcing it into punch card format simplicity. They're searching for the absolute simplest structural basis to hold a really complex multi-layered quantum state.
To really wrap our heads around how Qxbin achieves this level of simplicity, we have to look at the fundamental difference between standard computing and this proposed system. So classical binary is a linear chain. One character directly follows the next, a 1, then a 0, then a 1, kind of like beads on a string. But a quantum chain, at least according to the Qxbin theory, isn't linear at all. It's clustered. It relies on these multi-layered inputs and outputs that all exist simultaneously.
And this brilliantly illustrates exactly what we're talking about. The author visually maps it out. Up at the top, under binary chain, you see that straight line of individual circles, representing independent 1s and 0s. But look directly below that at the quantum chain. The circles are actually clustered together into groups. They represent a coordinated state of possibilities happening all at once. It's this really cool visual shift from a simple flat line to a dimensional grid.
All right, Section 3, the math of superposition.
Now that we've got the visual basis down, we need to look at the structural logic that actually holds those clusters together, the math that makes it work. If you look at the top paragraph here, the author specifically describes creating a process that is, quote, to a degree of Morse punch card probability matrix. Again, notice that intense focus on simplicity.
They are literally using the historical basis of Morse code and punch cards to frame a highly advanced quantum probability matrix. It's wild.
Okay, to make this complex fractional math a bit more digestible for us, we've broken the variables down into a really simple table. The core state is represented by I/O, so input, output. Then you've got n representing the top integer and m representing the bottom integer. By stacking these variables kind of like fractions, the author creates a notation system to track the multiple states of the quantum chain simultaneously. It's a completely stripped-down, purely mathematical basis for superposition.
Which brings us to section 4, the magnetic punch card.
So with the mass defined, this theoretical framework actually needs a physical form. This is where the author proposes a tangible hardware prototype. These scattered numerical grids, along with those distinct circular mappings, they represent what the physical layout of these quantum states might actually look like on paper. They almost look like little targets or compasses, right? Well, these are the proposed punch cards. Now actually scratch that. They aren't literally holes punched in paper like the old days. Instead, they are carefully mapped zones designed to hold specific clustered values. The author literally gives us the step-by-step instructions for building this experimental hardware prototype. Step 1, utilize the Hall effect simulation found in modern magnetic keyboards. Step 2, print a grid-based punch card system onto magnetized paper. And Step 3, record the quantum superpositions through those multiple coin toss states we were talking about earlier. By using magnetized paper and Hall effect sensors, the goal here is to read the really subtle variations in magnetic fields as clusters of data, instead of just simple on or off switches. It is just such an incredibly clever, low-tech way to simulate a profoundly high-tech concept.
Let's move to section 5 and see how this builds up. Personal quantum computers. Let's see how all of this simplicity, the coin tosses, the clustered diagrams, the magnetized paper, let's see how it all builds toward one massive endgame. At the very end of the text on the coin toss page, the author writes with just undeniable enthusiasm, unlocking a possibility of a personal qubit simulation processing system to build PQC. Now, PQC, in this context, clearly stands for personal quantum computer. The author genuinely believes that by reducing quantum logic to this punch card format simplicity, we can actually simulate qubits right on our own desks. That is an absolutely massive leap from a simple magnetized grid to a desktop quantum processor. So let's bring it all together. What are the key takeaways here? We just traveled through a brilliantly structured thought experiment. We started with the concept of Qxbin, that hybrid of quantum and binary logic, and we grounded it in the very simple basis of a coin toss. Then we looked at the proposed hardware, magnetized paper grids acting as modern-day punch cards. And finally, we discovered the ultimate goal, unlocking personal qubit processing, or PQC, envisioned by author Rupesh Malpani, looking ahead to the year 2026.
It really makes you step back and look at the technology sitting around you totally differently, doesn't it? Because if a foundational idea as simple as a magnetized punch card has the potential to simulate a qubit today, what incredible mind-bending leaps in processing power are going to sit on our desks tomorrow? The future of computing might just be a whole lot simpler and a whole lot closer than we think. Thanks for joining us for this explainer, and keep questioning the complexity of the world around you.